Hello, OAME members and Gazette readers. Welcome to a supplement of my column, What's the Problem? This video is meant to accompany my article from the June 2025 issue where I was looking at tons and tons of ratios. It turns out that for my article, I dug up way too many problems, way more than I needed. But I love my problems dearly and it was hard to give them up. So I'm going to talk about a few of the problems that I didn't talk about in the article. As well, I mentioned briefly the tool that I use to collect the problems from the CMC website, the tool that searches through their past contests and digs out problems. We'll take a look at that because I think it's a valuable tool for teachers, and it's a lot easier to talk about it in this format than writing it in the article. So I hope you enjoy this. First off, to the CMC website stuff. Let's take a quick look at that problem generating function from the CMC website. So if you go to the CMC website, cmc.uwaterloo.ca, you should end up at a page that looks something like this. And they have all sorts of resources for teachers and students out there. We're interested in the thing that'll be under Tools and Resources. If you click here, all kinds of things worth checking out, but we're going to look at the problem set generator. So clicking on there, it's going to create sets of problems randomly from Gauss, Pascal, Cayley, and Fermat contests. These are all multiple choice contests done by the CMC for grades 7 through 11. There's basically two options that we have. There's one that we're going to be looking at called the topic generator, where we can pick contest problems and generate them for our use or for our students' use. And they also have a contest generator at the bottom so that if you're practicing for a contest, you can randomly generate a contest, one of these grade 7 through 11 contests for student practice. But we're interested in the topic generator, so we're going to click on it. So here's the topic generator. So we have all these choices. So we have the various contests that we can choose from. Parts are sort of the sections of the contests. So the contests, these contests are broken up into three sections, sections A, B, and C, which sort of progress in difficulty. The sort of A has, especially at the beginning, some very straightforward and easily accessible problems. As we move through the sections, especially as we get into C, we get things that are a lot more interesting that fewer students are going to be able to do successfully, but there is some interesting things in there. Like even if a problem can't be solved totally, in a lot of cases, a lot of interesting thinking can be done on it. We have the topics, which sort of correlate a little bit to the strands, and then the secondary topics where we can look at specific types of things for us. So, for example, for the column that I was dealing with, I was dealing with ratios, so I selected only number sense type problems. In the secondary things, I got rid of the select all and I went to the fractions ratios so that all the problems that it would pick would only be dealing with those. At first, what I did was I kind of went through these grade level by grade level. Originally, I did 5 problems from A and B and none from C for each of the 5 groups. And then later on, I went back and did a document of just part C questions so that I could sort of differentiate between them and go through and pick and choose as I needed. So for example, if we decided that we wanted 5 part A and 5 part B questions for Gauss, that we're dealing with number sense and we're dealing with our fractions and ratios, I'd make those selections and then I'd generate a problem set. And when we do that, down below, there's our 10 questions. Now our 10 questions are set up and we see the question, we see the source, and so we see that this one was from the 2011 Gauss grade 7 contest, and it was question number 8, the primary topic and the secondary topic, and the same thing all the way through. These little arrows on the side allow you to actually fine-tune things. So if for whatever reason I didn't like this question, I could click on the side and it would give me a new one. Click on the side and give me a new one. Now, the only difficulty I saw with that is when you do your original, I'm pretty sure you're going to get unique questions. But if you start doing this, you may actually get this question duplicating something that you see later on. So you have to be careful with that. But you can go through and do your choices. When you're done, if you go to a printer friendly version, it'll bring you to another page where all of those extra things are taken off. So you don't have what contest it was from and all the topics and so on. You just get your 10 problems, and you can either print this off or do as I would do and just print it as a PDF, and then you can save it and use it whenever. If I go back here, we can also print off a solution set where the same sort of idea. You'll get a printer friendly version, but with the solutions to each of the problems as well eventually. So there's our problem, the answer, the C, and they show you how to do it. So great tool from the CEMC. Like I said, if you're looking for interesting problems, it's a great place to look. And by all means, don't limit yourself to the grade level that you're dealing with. For instance, when I was teaching grade 9, I would use contest problems from 9 through 11. I would look at them for sure and see if they're appropriate for my students. But in a lot of cases, a quite challenging problem for a grade 7 student becomes a nice challenge for sort of a bigger group of students at the grade 9 level. And similarly, you can take a problem that is from a grade 11 even and bring it down to grade 9. And again, using your teacher's judgment. In a lot of cases, if I would do something like that, I would actually tell them that, hey, this is a grade 11 question. I don't know if you guys can do it, but give it a shot. Knowing that it is basically at a level that the students could handle. So great tool. Check it out and for sure use it with your own teaching. Okay, the first problem we're going to look at is from the 2017 Cayley contest for grade 10 students. This is question number 15. We're going to look at the methods that we used in the article, just sort of as an extra example showing these things in action. And because we're doing this in video form, a lot of what would be written in a solution I'm stating, but you also get to see things in a little bit of a different way than if I was just writing it out in the article. So, a bag contains red, blue, and purple marbles and does not contain any other marbles. The ratio of the number of red marbles to the number of blue marbles is 4 to 7. The ratio of the number of blue marbles to the number of purple marbles is 2 to 3. And there's 32 red marbles in the bag. In total, how many marbles are there in the bag? So, again, we've got three things that we're dealing with here. We're given two ratios that look at two parts. So first we're going to look at this algebraically, which is maybe the standard way. So if I just use R, B, and P to represent the number of red, blue, and purple marbles, then this first ratio, 4 to 7, really tells me that I can write R and B as multiples of some integer, m, so 4m and 7m. Similarly, if I look at the second ratio, I can write B and P in terms of another multiple of an integer, so 2n and 3n for B and P. Again, these are integers because we're dealing with the number of marbles. But now we've got the blue ones match up. So these are both representing the same number of things, so I can equate those two variables. And really, I'm interested in how all three of these things relate, so I really want to use one variable. So let's write n in terms of m, which means that now, once we've got n in terms of m, I can go back to my purple stuff, which is in terms of n, use this, and write it in terms of m. And if I write it in terms of m, now all of my three variables are written in terms of m. So I can get the ratio of the three of those things. So it's 4 to 7 to 21 halves. Now, since we're dealing with numbers of marbles, these all have to be integers or whole numbers. So I can multiply the terms to get an equivalent ratio. Multiplying by 2 gives me 8 to 14 to 21. And now we can look at the information in the problem. We're told that there's 32 red marbles. I know that in sort of the smallest grouping that we could have, there's going to be 8 reds, 14 blues, 21 purples. So I'm going to have to multiply 8 by 4 to get me up to that 32. I have to do the same thing for the other ones, and I get my three numbers. This is going to be the actual numbers of each type of marble, and then I can just add them up and get my answer. Now, I didn't have to do this middle step where I got it as whole numbers. I could have looked at this and did the same sort of thing and multiplied everything by 8, but there's nothing wrong with cleaning things up. Okay, so let's look at a non-algebraic solution so that we can sort of compare them. Like if you always fall into the algebraic works fine, but sometimes it can be a little messy. So let's look at equivalent ratios, So like I said, we've got two ratios that are dealing with two of the three things. I'm really interested in how these three things relate to each other. So I can write out this first ratio as 4 to 7 to something. Same thing with the second one. I can just leave blank the stuff that I don't know. And I can actually take this 32 red marbles and put it down here. These are all representing the same things. These are all equivalent ratios. So we should be able to get them to match up. So if I look at first, I know that the reds match up here, and the 32 is the actual number of reds that I'm going to have. So I can go back to this and say, well, how can I get it to match? Multiplied by 8 gives me 32 and 56. So those guys match. That would actually tell me that this is going to be 56 as well. And I actually know how many blues I have as well. Going a step further, if I look at the blues here match up, these actually have to be the same thing because they're representing the same collection of marbles. The one on the top now is dealing with the actual number of marbles. This is reduced in some way. So I can bring this guy up to here by multiplying by 28. And in doing that, now these things match, which means that everything has to match, which means, again, I have my my numbers and I can get my final result. So depending on how we wanted to deal with the problem, you might be able to do this quicker, more efficiently by dealing with the equivalent ratios rather than going and muddling around with the algebra. Just something to think about. Finally, let's take a peek at using manipulatives. So again, this sort of gives you an opportunity to attack it at many different levels. Again, looking at my two ratios, blue to red is 4 to 7, so red to blue. So I've got 4 reds for every 7 blues. Similarly, I've got 2 blues for every 3 purples, so I can represent those as shown. But again, these are part of the same collection, so it's not 2 separate blue things. So when I look at that, I can think to myself, well, if I'm talking about the whole collection, the blues that I'm using in one part and the blues that I'm using in another part both have to be the same thing. So if I focus on one of them, I could say that might actually be the same blue marble that we're talking about. So we can kind of attach those guys together, showing that that's the shared marble. But again, every blue marble has to be part of one of these red ratios and one of these purple ratios, so we can fill things in so that all my blues are part of a red and part of a purple. I get my smallest amount here, and again, we can just count things out. This gives us 8 red marbles. Again, we need 32, so we could do 4 groups and get that, or we could just count from the first one, multiply by 4, and get our answer. The next couple of problems that we'll look at sort of have the ratio part of it as not the final result. It's part of the solution process, but there's something else going on that makes the problem more interesting. This second problem comes from the 2005 Pascal contest for grade 9 students. Question number 21. Integers m and n are greater than 100. M plus n is 300. Then m to n could be equal to which of the following ratios? So this becomes one of those cases where if I just look at the problem without the multiple choice part, there's lots of ratios that satisfy the information that's given in the problem. Basically, anything from m being 101 to m being 199. Those things all work and satisfy the conditions of the problem, but we want to know which one of these do. So it means I'm going to have to use some other information in order to do that. So let's first look at the first thing that they tell us, that m and n are both greater than 100. So that tells us that we know that m is greater than 100 and n is greater than 100. And we know that they add to 300. Well, if this guy is bigger than 100, and when it goes in with this guy, you get 300, this guy can't be bigger than 200, or can't even be 200. So we know that m and n are going to be not only bounded below, but bounded above. They have to sort of fall in that range of between 100 and 200, not inclusive. Now, if I took the first ratio and double everything, I get 200 is less than 2m is less than 400. Why am I doing that? Well, the fact that I've got these 200s in there, now I can relate m and n specifically. Because of that 200, 2m is greater than 200, which is greater than n. So now I know how m and n are related. N has to be less than double m. And there's nothing special about n. We could do the same thing for m, and we'd see that m is less than 2n. How does that help? Well, that means that if I've got to ratio these two things, the two terms, one term can't be more than double the other. So if I start looking at my results, A says, does 9 to 1 work? Well, in this case, m is 9 times m is 9 times n, which fails these conditions. So that gets thrown out. Similarly, 17 to 8. 17 is more than double 8. 4 is more than double 1. So as a result, I can throw out 3 of the 5 responses, and there's only 2 possibilities that we can check on. Now, how do we determine which of these to use? Well, now let's look at the second piece of information, and we'll look at our 2 cases separately. If I look at 3 to 5, it means that if I'm dealing with 2 integers, which it says here, this is reduced to lowest term. So sort of the smallest grouping that we could have has 5 of m and 3 of n, which means that we're dealing with 8 things in total. Well, when we combine the m's and n's, we get 300, which means I'm going to have a bunch of these groups. How many groups? 37 and a half. Now, because we're dealing with integers and we can't break this down any further, this half group is not going to correspond to integer values. So that's not an integer. It doesn't work. If we were a contest writer, we'd be done. We know that doesn't work. The only thing that's possible is the last one. We're good to go. Now, it's always a good idea to take a half a second to check to make sure that the right one works, just to make sure you didn't make a mistake somewhere else along the line. So if we look at that one and do the same analysis, it has 3 plus 2 or 5 parts. My 300 divided by that gives me 60 groupings of this 3 and 2. If I work that out, it means that I'm going to have 180 for m, 120 for n. Those do indeed add up to 300, and they are indeed in the ratio of 3 to 2. Each of them is greater than 100, so that's our result. Our last problem comes from the 2013 Gauss contest for grade 7 students. This is question number 25, so this is the toughest problem on the contest. So this is a nice challenging problem for students grade 7 and up, and maybe even lower. But there's enough in here that they can get started and think about some things and maybe even get towards a result. There's kind of a neat result at the end, and again, this is a problem that the ratios are built into it and are an important part of the solution, but sort of the final step needs a little bit of insight to get at. So let's take a stab at it. So again, we're dealing with 5 different types of things, and we're dealing with 2 different ratios that were given of collections of those, but we're interested in the whole group of tickets. So let's take those 2 pieces of information and look at equivalent ratios. The first one gives us blue to green to red. The second one gives us green to yellow to orange. We put those together. We put in some blanks for the things that we don't know. And keeping in mind that those are both describing the same situation, they're equivalent ratios, so we should be able to match them up. The only entry that matches is the green, and since they must be the same, we can easily deduce that we have to multiply that second ratio, the terms in the second ratio, by 2 to get 2 to 6 to 12, so that now these guys match up, which means that everything has to match up in that case. So we know that blue to green to red to yellow to orange is 1 to 2 to 4 to 6 to 12, which means that we're dealing in groupings of 25 tickets with 1 blue, 2 green, and so on. Now, if we go back to our problem, we know that we had 400 tickets in total. They're grouped together in 25s. So we have 16 groups, which means that we can go back to our ratio and multiply everything by 16 to get the actual numbers of tickets within each group. So we're most of the way here, and I think a lot of students could get this far. It's the next step that makes things a little bit interesting. So let's take our information and lay it out. We know that there's these many tickets of each type, but we want to pick the smallest number to ensure that we have 50 of one color. Now, you could get lucky and draw 50 and happen to draw the first 50 that you drew were yellows. That's not what this is talking about. This is one to make sure that we absolutely have 50 tickets of one type. Now, if we pick all the tickets, for sure we're going to have 50 of a type because we know that we've got more than 50 of some of them. But if we want to guarantee it, we kind of have to look at the worst case scenario. So if I go through here and I say, well, how many can I pick so that I don't get 50 of each type, and do the max of that. So if I go through it one at a time, if I look at the blues, I can actually pick all the blues and not get 50 because I don't have 50 blues. Similarly with the green, I can pick all of the greens and not have 50 tickets. If I go on to the reds, I do have enough there to make a group of 50. But if I only pick 49, I'm not going to have that 50. And the same thing with the yellow and the orange. So that if I look at this scenario, if I'm unlucky enough to at some point have 16 blue, 32 green, 49 each of red, yellow, and orange, I'm still not going to satisfy the conditions of the problem. So I can actually pick 195 tickets and not satisfy the conditions of the problem. Now, you might say, well, we want to satisfy the conditions of the problem. But now look what happens. What happens with my next ticket that I pick? There's no more blues or greens to pick, so it won't be a blue or green. It's going to be either a red, a yellow, or an orange. But because I've got 49 of each of these things, it doesn't matter which one I pick. I'm going to be put up to my 50. So if I pick one more ticket, 196, I'm going to have that 50 of each type. Now, the idea behind this is called the Dirichlet principle, after the German mathematician, whose name they attach to it sometimes. It's also referred to as the pigeonhole principle, because in a lot of cases when it's introduced as there's a number of pigeonholes or little homes for pigeons to live in. You've got so many pigeons. Is there going to be a case where the pigeons are going to have to pair up in order to go into it? And there's some really interesting problems in problem solving and in higher mathematics where this Dirichlet principle comes into play. You can do things like prove that there are two people living in Toronto that have the same number of hairs on their head using this principle, which might seem weird at first, but it's it turns out to be true. So if you're interested in this, if you go on YouTube, there's tons of things on Pigeonhole Principle, as well as elsewhere on the internet. I hope you've enjoyed these extra little problems and the article that goes with it, as well as looking into the CMEMC website and some of the tools involved in it. Until next time, happy problem solving.